Okay, we're recording. So finding something called the circular mill area. We take the diameter squared. So what we're going to do is take, okay, I'll just, so diameter squared in mils. Rectangular is width times height. And we're not going to convert into millimeters at this point. But so here's a nominal wire size. Here's the AWG. So these are really small. I'm going to scoop up until I see number 10. So here's number 10. The other thing to look at here is the strands, the number of strands. So basically we have, we'll go down to 10. We have a single strand conductor. And then we have 7 strands after that. And if you take a little any sort of circular thing like this, you make one circle, you take the same one, you put it right next to it, you see how many you can put around it. As in touching all around it, geometrically, it's 1, then 7, then 19, then 37, then 63, then 93. So those are our standard sets of strands. So in here, we're going to do a single strand, number 10. They've got in here 10,384. So the standard size for the CMA is 10,400. We just use that as within a few, 10,000. So that's what I put down on our sheet, 10,400. So quarter inch is in 0.250 inches. We need to convert inches into mils. So mils is 1,000. You multiply by 1,000, and that gives us 250 mil. It's just 1 L. So that's our diameter. And then we would square that to get our circular. So that we don't square inches, we square 1,000 inches, mil inches. So we're going to square that. And what does that equal to? You notice that I left a space in between 62, the thousands, and the hundreds. So this is the standard metric notation. The comma is in French is the same as a period for a decimal. So all of your ITA material will have a space in between the different units, between mega, kilo, units, and period. That and then spaces for building micro. Okay. So I'm trying to teach myself to do this. So quite often I'll do this, but sometimes I'll forget to put a comma in there if I'm rushing. If we knew that we had 62,500 circular mils, we could find the square root of that to find what our diameter is in mils, and then divide that by 1,000 to find out how many inches it is across. So let's do that with our 10,000. At 10,400 mils, let's find the square root of that. 400. 101.9. 101.98 mil. We're going to divide that by 1,000. 0.102. Yeah, that's right. That's going to be the diameter of that wire. Any questions on what I did? To record that precise, we just filled out number 12 on the diameter is it for it. And somebody in the back row. Circular mill or the mill diameter.
64.1.
Divide that, and that's going to be 0.064 inches down.
Any questions?
Yeah.
The fourth decimal place, or
Yeah, so this is a really good question. If when you're doing your calculations, keep all the decimals. Okay, if you're reporting to me, we're doing a class thing, give me 4 digits. Okay. 5, I can't. You give me 5, I'll lose the first one. Okay. So, and then you guys just store those numbers. And if you only do 4, you truncate it, and you truncate it again, you're going to end over here, your class is over here. There's a discussion about why you're different. Oh, I didn't store all of the numbers. Other discussion 50 times in the classroom. Burn up an hour of class time. Questions? So, so in a CMA table, for every 3 steps, we will have the CMA. Can you tell me what each step would be? Okay, you guys have from first year after. So I'm just going to put up here the cube root of 2 is equal to 1.2599 to 1.26, which is step. So if we go number 8, without looking at the chart, can you tell me what the CMA of that is? Bigger. That's a good. Sometimes that's all you know, right? You don't know the whole thing. Oh, I know it's going to be bigger. So then.
yeah, you have to do because you're going to have 2 steps. So you do 1.2, 2.6,
you guys are paying attention. 16,000. No. Yeah. But I wanted to put these little circles in here is that the bigger the wire, bigger the CMA number, and the lower the resistance. So in this formula here, KLCMA, where K is a constant for the different materials, the conductivity, it's ohms per mil foot. Length is in feet, and CMA is in circular mils, which is all these are imperial numbers. They're all in inches. There's another formula for metric. We're not going to use that right now. So K for copper is 10.4. And the K for aluminum is 17. So in here, if we do this formula here, if we say we've got 1,000 feet, number 10 copper, what is the resistance of that wire? 1,000 feet, number 10 copper. Here's my conductivity for copper, 10.4 ohms per mil foot. 1,000 feet, and I've got 10,400 circular mils. There is number 10, 1,000 feet of copper is 1 ohm. It's something to give you an anchor. One of my students, past students, said, you know, I wasn't clear on the anchors. So there's some people need something in an anchor you can always go back to and go from that. That's a lot. So maybe it could be one way you can study is what are your anchors, what are the key concepts. It's the change in resistance is equal to the original resistance times the degrees in Celsius change times the coefficient in here. And for copper, coefficient is 0.0040. On their formula sheet, it's 393. Was it? Another. So if we took this number 10 wire, and so this, the ohms per mil foot, this 10.4, that's based on 20 degrees Celsius. So if we, let's say we went from 20 degrees Celsius up to 40 degrees Celsius. Okay, so let's take, let's say this one here went from 20 degrees to 40 degrees. What is the change in resistance? We would take our 1 ohm times, and we went up 20 degrees, and times our coefficient.
That's 78.
Oh. Yeah, we're gonna talk about that right now here. So that's the change. And so what the new temperature is gonna be RO plus R delta. So we got 1 plus 0.0786 equals 1.0786. That's how much the resistance, the new resistance of that wire is given that temperature change. We are in a branch of electrical engineering, and this is engineering notation. So we do deal with, we do engineers. We're not engineers, but we are in the field of engineering. So scientific, or not scientific, but engineering notation. So this would be given to these three, given in millis. These ones here are micro. Oops, there's micro is here. Nano is here. And pico is there. So this one here is, this is to -3, -6, -9, -12. And so we're going to be using that. Yeah. I crammed that little drawing full of stuff, didn't it? So after lunch, we'll go back, we'll take